Hi students, in this lecture we are going to learn reflection and transmission of a wave at a boundary. See what is it? So we are taking here two different media. Medium 1. I'm taking different color for next medium. Let us take. Yeah, this is now second medium. So this is now boundary. This is now boundary. A wave pulse is traveling. Let us take a different color. A wave pulse is traveling towards right side. Let us consider for first one linear mass density mu1, and for second one it is mu, and both having same tension. So we are taking tension same. Okay, that means if you see speed of transverse wave, speed is given by v equal to root of t by mu, both having same tension, but mu value is not same. That means speed of a transverse wave is now changing on changing medium, right? So by seeing mu1, mu2, they are different values. Therefore, speed of a transverse wave is different. So at the boundary, what happens is, at the boundary, some energy transmits into second medium. That means the second string also starts vibrating. Okay. And at the boundary, remaining energy will reflect back. Remaining energy reflects. Now we have to focus. Let us take Y incident equation for instant wave. It is A incident sine omega t minus kx. Okay. So now we want to calculate for reflecting wave what is amplitude, and for transmitting wave also how to get amplitude. So this is what we want to focus here. So at the boundary, some energy transmits, remaining part is now reflects, right? So here I'm writing equation for reflecting one. Reflecting one equal to AR sine omega t, omega t. I'm writing here plus kx, not minus plus kx. Okay, wait here. It is, yeah, plus kx plus 5. This is equation for reflecting wave. And here for reflection, if you observe, we have taken plus kx because propagation direction is left side, but position vector is now right side. If you take now this as x-axis, this as x-axis, between k bar and position vector angle is 180. So after reflection means pulse is traveling, it is left side. Direction has reversed. So we have taken here plus. Okay. Or we can say directly. First one traveling along positive x-axis. After reflection, it travels along negative x-axis. Then we have to write omega t plus kx and plus 5. See meaning of plus 5 here. So here phi equal to 0 if mu1 is greater than mu2. See meaning of this. Mu1 greater than mu2. Mu value more. Mu value more means speed is less. And speed is less means it is denser medium. This is what we have discussed in earlier videos. If a speed is relatively less, then that medium is said to be denser medium. So here mu1 is greater than mu2. So mu is more, speed is less. So first medium is denser medium. When wave travels from denser medium to rarer medium, phi value becomes 0. Its meaning is that after reflection, there is no inversion of the pulse. I am showing here, making diagram separately. After, or let us take here only. So this is instant 1. When you take phi 0, that means there is no inversion of pulse. It will be like this. The meaning of 0. See, it is just like reflection of a pulse from a free end. Okay. Because this point is free to vibrate. That's why here no phase change. That means there is no phi value. It is equal to 0. Okay. So that happens when pulse is traveling from denser to rarer medium. Next case. So phi equal to pi if mu1 less than mu2. That means mu1 less means mu less means speed is more. So when speed is relatively more, that is rarer medium. So when a pulse travels from rarer medium to denser medium, there is a phase change of pi. And that is, see meaning of that. So meaning of that, this is instant pulse. After reflection, the pulse will be like this. It gets inverted. Shape gets inverted. The meaning of phi equal to pi. Okay. Next. Now let us take equation for transmitting one. Equation for transmitting one, that is equal to A transmitting. It travels in the same direction. That's why I am writing omega t minus, in the place of k writing k dash into x. See why we have taken k dash. So here medium has changed. When medium changing, speed is changing. When speed changes, so here speed equal to omega by k. When speed changing, k value changes because k equal to 2 pi by lambda. So we are knowing that frequency depends only on the source. So when medium changing, frequency does not change. But velocity changing means k has to change. Omega is a constant. So k changing because lambda is changing. Okay. That's why here we have taken k dash. Okay. So here you can observe omega for instant wave, reflecting also omega only because omega depends only on source. So here also for transmitting, we have taken omega only, right? So phi value 0 if traveling from denser to rarer medium, phi value pi if travels from rarer to denser medium, right? So mu1 greater than mu2 traveling from denser, right? So meaning of 0, there is no inversion of the pulse, instant pulse and reflecting pulse. Meaning of pi, after reflection shape gets inverted. Okay, right. Let us see here now notes once. Yeah. We have taken here y incident equal to a incident sin omega t minus kx, y reflecting, a reflecting sin omega t plus kx. This is plus because now after reflection, the wave propagates along negative x direction. Okay, plus pi. So mu1 greater than mu2. So traveling from denser to rarer medium. So phi value is 0. If you take reverse, traveling from rarer to denser, phase change of pi. Okay, right. For transmitting one, A transmitting sine omega t minus, because transmitting means it continues to travel in the same direction, that is a positive direction, minus k dash x. Why k dash means medium has changed. Since medium has changed, speed changes. Since speed changing, k changes, but omega constant. Okay, right. Now we want to calculate A incident, sorry, A reflecting and A transmitting. Okay, right. For that we require boundary conditions. See once the meaning of boundary conditions. Right. First understand meaning of boundary conditions. Medium 1. Let us take next one, medium 2. Right. This is now boundary. Right. Suppose at the boundary shape is now like this. Okay. Now focus. I will take different color here to make that. Let us take. Let us take yellow. Now focus carefully this point. Okay. So for that point, displacement of this point is taken as, see, one is traveling right side, instant wave. After reflection, reflecting wave, left side, right? And this is now transmitting one. So this displacement can be taken as displacement because of instant wave plus instant because of reflecting wave. See, we are taking here vector sum of two displacements. Okay. So displacement of this point because of instant wave and because of reflecting wave. Displacement of a same point can be taken as only due to transmitting wave. And see, we are taking displacement of same point in two different ways. I am repeating, we are taking displacement of same point in two different ways. Therefore, both must be the same. So displacement of this point is, when you focus left of this, one is incident and one is reflect one. Resultant of those two gives displacement of this point. That is what I have taken here. Y incident plus Y reflecting, that is equal to Y transmitting. This is one condition. Next one, at that point, if you are taking a slope, means tangent must be same. That is, we are taking here dou by dou x of y incident plus y reflecting is equal to dou by dou x of y transmitting. That means we are taking a tangent at that point, either differentiating the left part or differentiating right part. So we are finding same slope in two ways. Therefore, that slope must be the same. This is now second condition. So these we are calling as boundary conditions. These are known as boundary conditions. Okay. So with the help of these two, we are going to calculate what is amplitude of reflecting wave and amplitude of transmitting wave. Right, see here. Right, first one you can see boundary condition y incident plus y reflecting is equal to y transmitting. Now derivative of that, taking dou by dou x of y incident plus y reflecting, right? Means we are taking slope at that boundary. Then slope must be the same, right? These are now boundary conditions. Now by using these boundary conditions, we are going to calculate amplitude of reflecting and transmitting one, right? Okay. Now see, we have written y incident as, so I have taken omega outside, right? Let us see now once what we are doing. First consider, so what I am doing is here, let us take that boundary as x equal to 0. Let us take this boundary as x equal to 0 to make calculation simple. Right. See carefully. Y incident equal to A incident sine, I'm taking omega outside, t minus x by, take velocity in first medium as v1. Okay. Right. Next, y reflecting equal to A reflecting, A reflecting sine, take omega outside here, omega t plus x by, again v1, because reflecting in the same medium. I am taking here first case phi equal to 0. Okay. I am taking first case. That means traveling from denser medium to rarer medium. That means we are taking condition here denser medium, that is mu1 greater than mu2. Okay. Therefore phi equal to 0. Next, y transmitting equal to A transmitting sine omega t minus x by v2, because transmitting means medium has changed, therefore speed changes. So we are taking in first medium speed equal to v1, first medium, second medium speed equal to v2. Okay, right. So coming to boundary condition, first one, we are writing y incident plus y reflecting is equal to y transmitting, first condition. Now from this, see what we can do. Take x equal to 0. We are taking boundary as x equal to 0, that joint. So x is 0 sine omega t, x is 0 sine omega t, and this also sine omega t. So throughout both sides, sine omega t cancels. That means here what we get, A incident plus A reflecting is equal to A transmitting. Okay, equation 1. So this is when we are taking mu1 greater than mu2. So mu1 more, speed is less. Speed is less means denser medium. So denser to rarer medium, then A incident plus A reflecting equal to A transmitting. Right? Okay. Now, if you take condition, it travels from rarer to denser medium. Then see what happens. In this y reflecting, we have right here plus 5. That 5 value how much? Pi. Okay. When you take pi here, it becomes a minus sign, right? That means this equation becomes A incident minus A reflecting, that is equal to A transmitting. Okay. This is when it travels from rarer to denser medium. It travels from rarer to denser medium. Okay. Right. Let us take now next boundary condition, that is slopes, equating slopes. See derivative of, I am writing here, dou by dou x of y incident plus y reflecting is equal to dou by dou x of y transmitted. So I am taking a case, that case is phi equal to 0. Okay, I am taking this for phi equal to 0. Then see what we get. Derivative of the first one, it becomes minus ai by v1. Okay, we are taking derivative with respect to x. So its a coefficient is minus 1 by v1. So I have taken minus 1 by v1 into ai. Okay, and throughout the sine gets cancelled. Okay, sine omega t gets cancelled. Right. Next, derivative of y reflecting. Derivative of y reflecting, that becomes ar by again v1, right? That is equal to differentiate y transmitting, then see what we get, minus at by it is v2, medium has changed. So equation 3. Okay, so now solving equation 1 and equation 3, I am writing here, solve 1 and 3. We are going to get amplitude of reflecting wave and transmitting wave. Okay, so this is a way we have to use boundary conditions to calculate AR and AT. You can see notes here for that. So equations I have written. So boundary conditions, equations, right? See next one. So from first boundary condition we got A incident plus A reflecting, A transmitting, right? From second boundary condition we got this condition. After solving these two, 3 and 4, okay, then we are going to get A transmitting is equal to 2v2 by v1 plus v2 into A incident. A reflecting equal to v2 minus v1 by v1 plus v2. See here what we have taken. It is traveling from, see, mu1 greater than mu2, traveling from denser to rarer medium, right? That means mu1 means v1 less than v2. So here we have taken v2 minus v1 because v1 is less than v2, right? If you are taking second case, that second case is traveling from rarer to denser medium. Then we are going to get here v1 minus v2. Okay. So these are the results which we have to keep in mind. And this is a question asked in previous IIT long back when it was a subject. Okay.